So we're excited today to hear him speaking on something he's preaching for almost 10 plus years. So if you know Igor and you don't know about Koopman operator theory, there is a problem, okay? So he's going to be speaking on Koopman operator theory for dynamical systems, control and data analytics.
Thank you. So first of all, it's a pleasure to be here. This is my first time on campus, and it's really beautiful. I've been told that September is precisely the right time to come. I don't know if that holds, but probably May as well. I would have my guess. So I am going to speak about Koopman operator theory. The truth is, I actually wrote on Koopman operator theory in my thesis in '94. So it's been a long time. The reason why I thought this was an interesting framework for analyzing dynamical systems is you're going to see doing data analytics, doing essentially machine learning in a different way on dynamical system in the dynamical system context, doing aspects of control theory. That's an area that's accelerating pretty fast today. Was that classically dynamical systems theory is a geometry-driven exercise. So if you look at and if you have taken a class in dynamical systems theory, you have heard about stable and unstable manifolds. You have heard about chaotic dynamics. You have seen the Lorentz attractor, I presume. It was in movies too. So that's kind of what penetrates in the popular culture. But we had the ability to study relatively low-dimensional problems using very rigorous methods. And of course, a lot of the majority of interesting problems in engineering are very high-dimensional. If you can reduce them, that's a great thing, but the description should be, in principle, or the framework should be amenable to treating very high-dimensional data. So what I'm going to show you is an approach that instead of looking at state space variables, when you write ordinary differential equations, you write x dot is equal to f of x, and x is your state. Instead of looking at the evolution of state variables, I'm going to rewrite this as an evolution equation for observables, or rather an operator theoretic evolution for observables. And in that way, I'm going to lift the problem from a finite dimensional, possibly nonlinear, to an infinite dimensional context. So classically, this was used in measure-preserving systems. And interestingly, that dates all the way back to the 30s. And the reason why it got started was because of the fact that at that time, quantum mechanics was making big strides. It was becoming this new physics that was very interesting. And it was driven by an operator theoretic approach. And then, as you will see, there was a quiet for a very, very long time. But I guess what is really interesting to us, most of the background in this room, I presume, is in engineering, physics, biology, I don't know, somewhat applied science fields, is dissipative systems. Almost everything that we look around us at the larger scale is dissipative. And so there was none of that. So for dissipative systems, there is an object in mathematics that's called a composition operator. And I'll describe to you what it is that extends this classical notion. So we'll concentrate on that. And so you will see that when we lift from nonlinear to infinite dimensional linear, if I told you I have a linear operator or a matrix, you would immediately with the education that you have, you would immediately ask me back what are the eigenvalues and eigenvectors. Maybe some of you would ask what are singular values, right? But that's your first thought, and you will see that so what I like to show to you in the context of the presentation is that doing infinite dimensional linear algebra is a good thing. That you have algorithms and that you can actually have success in understanding high-dimensional data, dynamical data, in the context of that particular approach where you worry about the spectral content of your evolution. The operators that we'll get are non-self-adjoint, so this is different than quantum mechanics. If you studied any quantum mechanics, then you have been primarily interested in self-adjoint operators. So that brings with itself a lot of complexities. They might have something that's called continuous spectrum. I'll describe all of this. Maybe the most important point is the one at the bottom. Dynamical systems classically requires a model. You need to write ordinary differential equations to find what your stable and unstable manifolds and so on and so forth. This does not. You can actually extract or find stable and unstable manifolds, whatever you need from your dynamical systems context, using a data-driven approach. So you can just get given some data from dynamics, and you can call on the classical concepts in dynamical systems now in possibly very high-dimensional spaces and proceed. And that perhaps is, for someone who is in dynamical systems, a very attractive feature. Certainly was very attractive to me when I first recognized some of the context. So what does that lead to? Well, this is a paper from 2009 that Clancy Rowley, myself, and a couple of other people did. And this was one of the first applications of a paper that I did in 2005, which was purely theoretical, very ergodic theoretical, operator theoretical, where we said, well, basically, OK, let's look at this. This is a nonlinear, well, Navier-Stokes driven flow out of an orifice that is also affected by a shear flow in this direction. So if you've seen a chimney spewing out white smoke and angling in one direction, that's kind of what you're looking at here. And you're seeing that that evolution is very complex. And if you remember your standard dynamical systems class, you would say, well, there is no way that there is any superposition here that I can put together various modes and put them together so that they actually have a dynamical meeting that actually does get that complexity to a very fine accuracy. And it turns out this operator I'm going to tell you about has eigenvalues in the discrete context on the unit circle. Here you're looking at the computation of a linear infinite dimensional operator on a nonlinear infinite dimensional problem. I know it sounds like a lot. So you might be asking yourself, what can I do with this? And the trick is going to be that you never want to look at the operator itself, that you want to find computational methods that avoid exhibiting the operator. But if you find that, if you have a methodology that finds its eigenvalues, a lot of these methodologies are today known under the name of dynamic mode decomposition that you might have heard about. This is a class of methods that under certain conditions computes the eigenvalues of that linear operator that I'll define. And here is a complex conjugate pair. Here is an eigenvalue at 1. You can prove that there is always an eigenvalue at 1. That corresponds to the mean flow, time average flow. And here is another. And those eigenvalues correspond to certain modes that you can also relatively easily get from the flow evolution. Right? You solve Navier-Stokes, you're really looking just at the data. There is no Navier-Stokes involved in obtaining, well, it's post-processing of what you're looking at the top. And if you take a look at these two complex conjugate pairs, one pair corresponds to this spatial shape, and the other pair corresponds to this spatial shape. And now you're seeing streamwise vortices, cross-stream vortices, vortex rings on the core of the jet. You're seeing physics, right? You're seeing physics out of this abstraction of going to an infinite dimensional space. So unfortunately, now I told you my whole talk, which is we can I can go home and basically enjoy the rest of our day, except that I'm going to do a lot of technical stuff that's going to describe how do you get from A to B, but that's the core of our current understanding of the subject, that you have this infinite dimensional operator, you compute its eigenvalues and eigenfunctions, eigenmodes, and that is representing some of the physics or biology or whatever other data you have. Some of the interesting concepts between your data are captured by these calculations. And so what is of interest today, we're still developing aspects of attractor theory, so not measure preserving as classically 80 years ago. We are working on hybrid systems. I had a really nice set of discussions on hybrid systems today. High dimensional applications, if you look at the references on this, you will see that there is really a large number of applications in fluid dynamics. Some, and pretty large and growing in power grids. We've applied it to energy efficiency in buildings and even have a few patents on the subject. But many, many other data-driven analysis of various processes are, at least people attempt to compute and see what this particular methodology gives them. So I won't name all the different applications. There is a large and growing number. So why do we need to switch, in some sense, the point of view in order to be able to analyze these high-dimensional systems? Well, classically, there are really kind of three different ways we looked at dynamical systems in the past. One of them is mass spring, write the solution in terms of position and velocity versus time, call it a day. And I would call that Newton's point of view. That was extremely successful for a long time because the two-body problem could be solved until Poincaré figured out that the three-body problem cannot be solved in this way in a very precise manner, right? You cannot get a closed solution that depended on time. And that led him to say, well, why don't I plot, or rather look at position versus velocity? And that plot is very different, right? There is no time involved in it, and the harmonic oscillator has an ellipse, or mass spring system has an ellipse associated with it. And so that turned out to be a great representation in which to study complex processes like the Lorentz model of the convection in the atmosphere, which is really three equations, famous three equations that give you this chaotic attractor, butterfly effect, whatever you want to call it. But if you look at this, there is an even simpler way of representing a harmonic oscillator or mass spring system, and it's basically a spectral view where you say, well, it has frequency omega, amplitude A, and phase phi. Three scalars, and you're done. So the compression of information in the spectral point of view is tremendous, right? If you know these three numbers, you're going to know the evolution of the system. At first sight, these three all look very, very, very different. So let me introduce the fourth one, and that is this dynamics of observables. Instead of the state space, you say, well, is there, if I get any arbitrary function of x and x dot, can I say how that evolves in time? And you all know the answer for some specific cases. So for example, perhaps the most interesting and important observable on all physical, this is a big statement, but I think it's true in our own livelihoods, is energy, right? Certainly on TV, I'm going to hear energy today probably 15 times. Energy is a function of position and velocity, and it is in the context of mass spring system characterized by the fact that it's conserved. So if your energy is labeled by E, you could say E dot is equal to 0. And that's, I'm looking whether I have any space to do a little bit of blackboard, but I don't. E dot is equal to 0. And so that has extremely simple dynamics. That's much more complicated than E dot is equal to 0. And if you pick up another variable that is the phase, you're going to get phi dot is equal to omega. Yes? And so now you have a reduced set of equations. E dot is equal to 0 and phi dot is equal to omega that give you quote unquote the best variables, right? One tells you that the trajectories, the energy is constant on trajectories, so that labels trajectories, and the other one is telling you the time. Phase is just reduced time. Interestingly, both are eigenfunctions of the operator that I'm going to introduce to you in a second, right? So on the basic physical problems that you look at, there was this hidden set of concepts that is behind pretty much every simplification that we have done, that is actually the content, spectral content of what Koopman discovered, and von Neumann, being the genius that he has figured out immediately, is very interesting and important, and applied it right away to prove what is called the mean ergodic theorem. So let's do just a little bit of the setup. So we're going to have observables on phase space. So our phase space is going to be M. That's, let's say, a manifold, but it could be Rm or whatever it is. And I'm intentionally going to pick observables that go from F to complex numbers. The reason being that as soon as you're talking about eigenvalues and eigenvectors, you should really go to complexification rather than stay in the real space. So remember, one of F's that I could have picked in the harmonic oscillator case was energy. And here is the definition of the operator. If T is your map from M to M, so now I'm discrete time. Let's say I have a system and I discretized it and I'm just sampling it every time 1. Then U is the operator that acts on the function F by composing it with the map. So if you've studied fluid mechanics, this is the Lagrangian point of view. You're sitting at some initial point X, you make one step, and you ask, what's my pressure now? And if you find that pressure in one step, you pull it back and say, okay, the pressure the next time is there, but the function that I'm defining is by pulling back that pressure and associating it with the initial condition. You're sitting on a particle, and you have a static field of particles, and you're looking forward. So physically, this is what's happening. What's happening here in the time, in the continuous time, of course, STX is just the position of X after time T that has evolved in your state space, and it's also the composition operator. I hope that everybody can see. I would do it on the blackboard if I had a little bit more real estate, but if you add F and G, because of associativity of the composition, U is actually a linear operator, right? And then multiply by a constant, obviously, constant is not going to change anything, yes. So U is actually a linear operator that tells you that you should worry about its spectrum. I didn't say eigenvalues for a very particular reason that I'm going to tell you. And this is a long story back in 31 and 32. It's just that, interestingly, Koopman and von Neumann actually did utilize the spectral point of view for measure preserving systems, so things like Hamiltonian systems. But somehow between 32 and 90s, it was languishing and it was not used very widely. Let me be even more precise. Let's say that we have just x dot is equal to f of x. You can always generate this evolution here by an advection equation that looks something like this. Yes? This side here would be a generator. And if you ask for the eigenfunctions and eigenvalues of the generator, if phi satisfies this equation, then ut is going to satisfy by spectral lifting or the spectral mapping theorem this equation here. So eigenfunctions and eigenvalues of the Koopman evolution are going to satisfy this. Now, what are the complexities? First of all, x dot is f of x is not the last thing I want to solve. I could have hybrid systems. I can have Navier-Stokes. I can have whatever I want there. It could be infinite dimensional. I can still define the operator that I talked about before. This equation then I can't even write down. Well, it's a functional equation. Hopf wrote it down a long time ago, but just writing down the equation, as I argued, is not necessarily a good thing, because it's just a complex equation it's an infinite dimensional equation on an infinite dimensional state space, right? It's not necessarily the best thing to do. The task is to find the eigenvectors and eigenvalues, or eigenfunctions and eigenvalues, without writing down that evolution equation. So here are some outcomes. If you find those phi's, the level sets of these eigenfunctions are meaningful for the geometry in the state space. So if you have background in dynamical systems, stable and unstable manifolds, invariant sets, all of this stuff can be computed by trying to find phi's that satisfy this equation with this operator. Example, I just gave you one. If I have a Hamiltonian system here, then f dot grad E, where E is energy, is precisely 0. Energy doesn't change in the direction of the vector field for a Hamiltonian system. Yeah? So that would mean that energy itself is the eigenfunction of the operator here, with lambda precisely equal to 0, or in the discrete time case or continuous evolution, this right-hand side having 1 right here. So evolution of energy gives me back energy. If I go one step forward, energy doesn't change. Yes? So what happens if I have energy for the harmonic oscillator? I plot the level sets, and I get trajectories. You see the geometry coming out of level sets of a function. And that's the key idea. Every single eigenfunction of the operator that you have has a geometric meaning through the level sets on the state space. You go from this lifting back to the state space to get geometry in the state space. Besides, if you now take those eigenfunctions and project your evolution onto them, that's going to give you something that's called Koopman modes. I'll give you a physical intuition of Koopman modes, but for now I'll tell you that if you have a linear system with linear observables, Koopman modes are nothing but eigenvectors. So they limit to eigenvectors in that case, which should satisfy you too, because you've seen this before, and then you have this vast generalization that works for an arbitrary nonlinear system if you have any eigenfunctions. All right, so here is the lifting. This is really a lifting from a state space to a space of observables. If you start with some point P, and you say that your observables X, think about your Euclidean space as basically a space of points rather than X, Y, Z. Then X, Y, and Z are in fact observables. If I pick a point, I can attach an X to it. This was Descartes' original thought, right? I don't know if you know that anecdote, but apparently he liked to lay on a couch a lot, and then he was watching a fly going around on the wall, and he said, well, if I measure it this way and that way, I get 2 coordinates, and I can tell where the fly is, and that's how coordinates came about. I don't know whether this is true or not, but it's kind of influential in what I'm trying to tell you. Consider the space of all the points P on the wall, and then attach X and Y to it, and you're going to see that you're actually defining a function, an observable on the wall, right, that actually associates a number. So here is X of P. Suppose that now you have a basis of functions on this state space, F1 to F infinity. So let's say that space is a Hilbert space. And then you can expand your functions in terms of that basis. You lift it up. You apply a linear operator to that basis. If the linear operator is bounded and nice like the Koopman operator is, it's basically a big matrix. So whatever basis you have, you multiply them by some coefficients d, j, k. OK, that gives you the evolution one step forward. So now you have the future function up here, the future mapping of the basis function right here. If you sum those mappings up, look, X is just Cj, Fj, you're going to get a representation in this space down to the state space, right? So this is how you go up and then down. So this is a commuting diagram that tells you how the infinite dimensional version of this is related to the finite dimensional version of this. Note that I didn't say anything about smoothness. I didn't say anything about dimension of the space. I didn't say anything about anything. The only thing that I had is a mapping. X prime is equal to T of X. So if you thought from the previous slide, oh, this is the advection diffusion equation, let's think again, because I've had a hybrid system where I have something else. I can perfectly fine do this, define the eigenfunctions, eigenvalues, everything else with this lifting without worrying about smoothness or really anything else that we are worried about in the standard situation of ordinary differential equations. So what do you do next? I mentioned spectrum already 73 times, probably, if you were counting. The right thing that you need to do next, which is if you look back at some 2004, 2005 papers of mine, this appears. So if you have a system on the attractor, then G is your set of observables you're interested in. Think energy in a fluid, think pressure, think velocities, think whatever you want to put into that vector. It splits into what is called a singular part and a regular part. I'm shaking my hand because you see that regular is singular and singular is regular a little bit. But the point is that this part here that is called singular is composed with term that is just the time average of the process. So that's the first term that you get. And that's related to invariance like energy. That's the first term. The rest of the terms are related to other eigenvalues, if you have any. So lambda j's are eigenvalues. And this part here is the residual. So if you think about it in a more general context, when you have dissipative systems, let's suppose you're going to a fixed point. This would be just the value of your observable at the fixed point. This would be the expansion in terms of maybe approach to the fixed point. And this would be 0, because you don't have any continuous spectrum, generally speaking, in that case. If you had chaotic dynamics, this would be the average on your attractor. This would be combination. This would be combination of decaying modes, so anything that goes towards the attractor. And this would have what is called continuous spectrum. It's an integral over many frequencies. Yes, so instead of a sum, you get an integral. All right, so there are 3 interesting objects if you're interested in the singular part, or I'd rather call it the point spectrum part. If you find some eigenvalues, then eigenvalues are interesting because they give you timescales. Eigenfunctions are interesting because they give you level sets in the state space, so they're state space objects. And then these guys here, you see x is in state space, so x dot is equal to f of x, and z is just some label. Z, for example, could be spatial coordinates in a 3D fluid flow. So you would label each velocity component with z, which is z1, z2, z3, just the spatial point. So you can view a fluid flow as basically a collection or a family of observables that are indexed by z. Yes? So that's why this z sits over there. And that's why G star has dependence on z. Let's say you settle on some attractor. Your time average of velocity is different at this point than it is at that point. And that's why the eigenfunctions are functions of x, of state space, but the modes are only functions of z. So you see you have double decoupling here. One is that you have decoupling in the time versus space, state space versus time, yes? But then you also have a decoupling between the indexing of your variables, which is in z, and the indexing of the state space, which is in x. And then this is the continuous spectrum part that might come from chaotic dynamics or just from the fact that you have different frequencies on different trajectories. Okay, so most of the applications have been concentrating on the fact that if you extract these guys over here that, as I said, are analogs of eigenvectors, you get some interesting spatial shapes. Here is the temperature in a building in Santa Barbara, which has a particular 24-hour mode. Every building has, building dynamics does not necessarily seem very exciting, but actually, if you look at it over 24 hours, or the fact that you might have a seminar here every week at, 4 o'clock, people come in, the heat goes up, and you see that periodicity on a weekly basis. So there is actually a lot of eigenvalues of the associated Koopman operator, and the field of observables is all the temperatures, right? So here is what happens, and you see it's quite non-homogeneous in this particular building at UCSB. There's a lot of work, and I'll show you some that's been done on power grids, fluids, evolution of flu, propagation through the United States, and so on and so forth. So let's now go, let's now go to a little bit of discussion. Oh, that's interesting. Oh, I want to say one more thing. This is why this is spinning. If you have control, then you can easily add a of xu, where u is your control, into this equation, and you'll see that it retains kind of its nature, except that it's bilinear here. Yes, it's bilinear in state and control if your a of x is actually a linear variable, right? So it's, all right, so I already said that. So let's go to eigenfunctions a little bit. I argued that eigenfunctions are important. There are some really important mathematical properties of the eigenfunctions that tell you that just from a finite number of eigenvalues, you can get all of them. Because one of the questions that you might want to ask is, okay, you just told me I need an infinite number of values to describe a finite dimensional nonlinear system. That doesn't sound like a good deal. So this is a nice algebraic property. It's a little bit mathematical, but it's kind of easy to understand. So if you have eigenfunctions phi1 and phi2, under certain assumptions, if you have a vector space of observables that is closed, and you have a constant function in that space, so you should make sure that your observables are sort of a correct space. If phi1 and phi2 are eigenfunctions, then their product is an eigenfunction too. Yeah? So the product is an eigenfunction with eigenvalue that is the sum of the eigenvalues of the individual functions. What that means that if you have an n-dimensional finite, nonlinear problem, if you find n eigenfunctions, you will find all of them. Or rather, you found all of them just by products. So it's a tensor product construction, which, of course, we all know in machine learning is a very useful thing to have, right? This theory has it naturally embedded in. It's not enforced in any possible way. It's actually how the operator comes out to be. And so I'll show you some consequences of that. But before that, let me just tell you what this is for linear systems, because I think that's the first thing that one would look at. So you can compute for a linear system x dot is equal to ax, the eigenfunctions explicitly. They are inner products of x itself with the left eigenvector of A. So defined very precisely. When you get a spectral expansion, and I normalize them, they're normalized, not and orthonormalized, right? So they're dual basis, Vj's and Wk's, and they satisfy this particular equation. So now the expansion that you're used to is that x of t is this right-hand side with some constant over here, yes? This is what we learn in linear dynamical systems theory to start with. And that constant, we are told, is a function of initial conditions. It turns out that that constant is precisely the eigenfunction of the Koopman operator associated with the eigenvalue lambda j in that case. And that's nice. It has a geometric meaning, actually, because remember, the level sets of Koopman eigenfunctions are meaningful. So in the linear systems, there is this expansion that I'm confident you have seen many times, and yet there is a little bit of a new interpretation. And Vj's here are the eigenvectors. Those are the Koopman modes in that case. So if you have linear observables, just x itself, on a linear system, Koopman modes are eigenvectors, and these constants of initial conditions are in fact the eigenfunctions. That actually gives you a nice, if you're a dynamical systems person, this is a nice realization. And that is, if you took a class in dynamical systems theory with stable and unstable manifolds, so stable manifolds are all collection of points that go towards the fixed, well, let's say fixed point. I have a fixed point in the system, and then unstable manifold is a collection of points that go backwards towards the fixed point as time goes to infinity, and we are used to defining them as, for linear systems, as the span of the stable or unstable eigenvectors, yes? Now, from the previous construction, look at this. If I have lambda, if I collect all the lambda j's that have positive real parts, and I say that associated phi j's are precisely 0, then in fact I have characterized the stable subspace. Usually is the span of this guy. I'm saying a more natural definition is the 0 level set of the associated eigenfunctions. Why is this important? If you want to do the same in a nonlinear system, you would need to linearize close to the fixed point. This requires no linearization, even for a nonlinear system. You just set the eigenfunctions to 0, and you'll get the appropriate object. So that's something that is quite useful. If you don't have geometric multiplicity equal to algebraic multiplicity, things works out with more complex formulas, but you can deal with non-normal growth, if any of you are interested in it, and so on and so forth. That's the story of what this means for linear systems. Here we actually have the concept of generalized eigenfunctions rather than the normal. So how do you extend this now to nonlinear context? First of all, let's talk about the situation in which you have y is equal to f of x, which is where f of x is nonlinear. Then the Koopman eigenfunctions give you actually a transformation of variables. A transformation of variables to Jordan form if you write f tilde as just a function of x of phi, that's a transformation, then you can write an expansion of UTF as a sum. Remember the products of eigenfunctions? Those are eigenfunctions again. As soon as you have a nonlinear observable, let's say you have x squared, and your system is x dot is ax. If you have a nonlinear observable, x squared dot is 2x times x dot. That's 2a x squared, and so therefore there is an eigenvalue that is 2 times a. That story generalizes. Look at the eigenvalues here that are computed explicitly. They are lambda j's, which are the eigenvalues of just the linear part of the system, times nj, where nj's are integers. And then the Koopman modes can be computed also explicitly as these nd order derivatives. So in this case, it's completely analytic, what you can do. But also, from considering the eigenvalues lambda 1 to lambda d, you start considering eigenvalues that are also integer multiples. So n1 lambda 1 plus n2 lambda 2. Those are also the eigenvalues that you need to worry about, and they're meaningful in the context of the nonlinear evolution. So how do you couple the two? Well, the standard way of coupling the linear and nonlinear evolution is to represent any nonlinear evolution that you have with a linear one, and the eigenfunctions themselves enable you to do that. And that's precise. So you can linearize the system without really linearizing it. Linearization for us usually means take some f of x and then look at f of x plus delta x and expand in Taylor series. That's not what I mean, right? What I really mean is a conjugacy to a linear system where the eigenvalues stay the same. So whether you're looking at a linear system or nonlinear system, the eigenvalues stay the same, and the eigenfunctions are just a composition of the eigenfunctions that you find for system A composed with transformation. So you have a really nice invariance. So if you're looking at a bunch of different sets of data, the eigenvalues under different observables are the same. And if you look at our paper on data fusion some years ago, that can be used very effectively in trying to do prediction in high-dimensional systems. So conjugacy is one of the things. I'm not going to go through the proof of this, but I'm going to make just one step further, and then I'll kind of tell you the whole story, because the next thing up in the complexity of dynamical systems, attractors from fixed points, is a limit cycle. And hopefully everybody's seen something like the van der Pol oscillator that has a limit cycle. And so it turns out that you can map this kind of a dynamics into a two-dimensional system that has s dot is equal to 1. That's just the phase. But it's a global phase. Anywhere in the state space that you are, that phase is actually defined. And then you have y dot is a of s, that depends on phase, y. That looks like a linear system. It's just modulated by s. So you can derive the eigenvalues of that too. It's a little bit more complex than what I've shown you before, but here is the crucial point. So if you find the eigenvalues on the limit cycle, and eigenvalues of the limit cycle that I'm going to define in a second, then integer multiples of eigenvalues of the limit cycle plus I integer multiples of eigenvalues on the limit cycle give you everything. In other words, for these kinds of systems, you actually know a priori the eigenvalues. You know them. If you have a limit cycling system, the only thing that you need to find out is the Floquet exponents and the omegas, which are really related to the period on the limit cycle, and you'll find everything. And what does that look like in practice? If you're looking at your data and your eigenvalues after you ran DMD look something like this, you're actually going to know that you have a limit cycle in your system. No need for a model, no need for anything, purely data, run it, do something like DMD or something else, make sure that the noise doesn't screw up the eigenvalues. I mean, be careful about how precisely you do it. And if you see something like this lattice, then actually you can identify the system as having a stable limit cycle, because everything, these are the eigenvalues of the Koopman operator all of them are in the left-hand side, and there is a theorem that says that if you have n eigenfunctions for which eigenvalues in the left-hand side, then by the composition that I told you about, your system actually has a globally stable attractor, in this particular case, a limit cycle. Okay, so I wanted to show you, I wanted to take you quite far in the context of some of the basic theory, because of the fact that when you do computations on data that is noisy, there is something to hold, to put your hat on. And those are these basic theorems as to what should you be seeing if you have type A dynamics, type B dynamics, type C dynamics, and so on. So let's now go and say how is this done in practice. So one of the ways you can actually get the projections is by pure weighted averaging log trajectories. And that's my favorite method, but it's not the method that is most used. I get the most insight out of that. It basically says if you have a signal that is limit cycling and it's at frequency omega, multiply it with e to the minus I omega t. So check the resonance. And if that gives you a non-zero number, you have an eigenfunction or a mode, and that actually computes the modes. It's a little theorem that computes the modes. So let's compute the modes. In this particular problem, there's a fluid flow. 10,000 Reynolds number gives you a steady flow in a cavity. This is a two-dimensional fluid flow, just a cross-section. Here is what the dynamics looks like. A big rotation in the middle and a bunch of shear type flow on the side. And now what we're going to do is we developed a nice refined, so this is my former student, Hassan Arbabi, who's now a postdoc at MIT. So he did a very, very careful computation with the formula that I have shown you before in order to get the spectrum. The limit cycle should have a spectrum, if I'm not considering the decaying modes, that is the base frequency and harmonics, yes? Just like in Fourier analysis. And here is the time average. Remember, the first mode was the time average. It kind of looks like the steady flow, but this is time periodic. So between 10,000 and 13,000, the flow goes into a, if you measured at every point, you would get a time oscillation, yes? So this is time periodic. Look at how much this one looks like that one, yes? But this is the time average of flow at 13,000. This is a steady flow at Reynolds number 10,000. And this is the first mode corresponding to that frequency. So let's go a little bit further. This is 16,000. Now we're going, look at the spectrum. It goes from that lattice that just n times omega to n1 omega 1 plus n2 omega 2. It's a little bit more complex to figure out that it's exactly that. But there are two base frequencies here, and everything else is driven by those two base frequencies. And here are, so because there is an extra eigenvalue, there is an extra mode. But look at this. We changed the Reynolds number by 3,000, and look at that. Do they look the same to you? Pretty much, right? The shape. And this is a new one. Okay, let's go on. 20K. Now the spectrum is starting to look like it's continuous, except that it does have these peaks. Here is the eigenvalue 1. Here is the eigenvalue omega 1, omega 2, omega 3. Again, look at the similarity between these guys. And at Reynolds number 30,000, still the features that you're looking at, maybe a little bit lighter, but remember, eigenvectors don't care whether you multiply them by a constant. So the color shade can go in and out. That doesn't matter. But look at the shapes, and you will see the same. So what is the moral of the story? The moral of the story is that in this particular problem, I don't know whether this is a general feature at this point in time, because we don't have we have a set of conjectures as to why this occurs, is that you can essentially learn this library from one of the flows, and you can apply it to all these other flows at various Reynolds numbers, and you're going to get a good result as far as the prediction is concerned if you just pick those modes, right? So you don't need to learn a new set of modes for every single Reynolds number, which in principle is the case, right? This is a continuously varying family. For some reason, this family seems very discrete in nature. Some of you are working on really complex problems, or the fluid flows or combustion or stuff like that. Actually, we talked about this. It would be fantastic to see whether, what is the breadth that this holds in. But for learning, this is, of course, a beautiful characteristic, because the reduction is between 10,000 and 30,000. That's a pretty nice span of Reynolds numbers in which you can do a reduction like that. The most popular method for computing eigenvalues, so I'll tell you the difference. In the previous methods, we didn't get the eigenvalues to start with. In the method that I'm going to describe, DMV, you get the eigenvalues and modes at the same time. In the previous method I described, you're searching for eigenvalues carefully, and then you carefully refine and carefully project. And there are theorems that tell you that your project, the generalized Laplace theorem tells you that is correct. If you actually do it properly, you will get the projection. You will get the Koopman mode, right, in the limit, if you take enough samples. There are theorems that say that. Here, the advantage of dynamic mode decomposition, which was originally derived by Peter Schmidt, completely outside of the concept of Koopman operator theory. Didn't have anything to do with that. Peter just said, look, if I have an evolution that is a sum of exponentials, this is how I can get the exponential exponents from data. That was his approach to the problem. And then we realized that there is a connection between the two, because remember, my spectral expansion had these exponentials in there, right? So there is a clear-cut connection between the two, even for the nonlinear case. So anyhow, here you have snapshots, F1, F2, F3, and so on. And each snapshot is carried to the next point in time by the Koopman operator itself. That's by definition. Remember, time step is, Koopman is just your observable composed with a step. So you compose with 2 steps, 3 steps, and so on. You get a sequence of snapshots. And then the nth step, you're saying, if the nth step is linearly dependent on the previous ones, you can express it like this. And then you can represent everything in a finite dimensional space with what is called the companion matrix, where you need to define C0 to Cn minus 1. So if you do that, you have a reduced representation U tilde. And let's find lambda tilde and E tilde, which are the eigenvectors and eigenvalue of the reduced representation. You can do a little expansion here, and then apply through U. That's U tilde. That's a reduced representation through U to E tilde, which is the eigenvector of this reduced representation, times whatever your set of observables is. And you'll find that it satisfies this equation. Let me rewrite it a little bit and tell you what it is. Look at what it is. Operator acting on something minus some scalar acting on that same thing, the norm is equal to the right-hand side. Suppose that the right-hand side is very, very, very small. Then this starts to look like an eigenvalue, eigenvector equation, yes? So indeed, what you can say, at least, is that this part here is clearly the equation that says that E tilde dot F tilde is in the pseudospectrum of U, yes? For epsilon of the pseudospectrum is En minus 1R. So it's not quite an eigenvalue, but under certain conditions, when you go with a large number of samples, it will actually, the pseudospectrum is going to collapse, right? So that's basically what you're doing. When you're representing the Koopman operator with a companion matrix, like all these DMD methods start from, pretty much, this is what you're doing. You're essentially computing the pseudospectrum. Now, the epsilon in the pseudospectrum might be bad, and that's what you need to worry about. But there are theorems that tell you that the convergence actually exists. All right, so that's that. And the last 5 minutes, maybe? Is that OK? So the last set of things that I want to tell you is about control and another application in power grid. So you can extend this to control systems. In a control system, the next value that I'm going to see depends on the state I'm at and some applied control. Yes, U. So the way you adapt this to Koopman operator framework is you expand that system to have the dynamics of U itself, right? Because U changes in time. Your control changes in time in a certain way. So you can define the dynamics on U as well, and you expand the space to encompass both the state and the control in a state space. And now you're good, because there is a Koopman operator for that. So you say, And there is a number of other works that don't quite use the same formalism, but this from Koopman operator theory perspective, from our point of view, is precisely the correct formalism to use, and I'll show you the success of this. So this is Milan Korda and myself in this year in Automatica. Now this is sort of the least squares problem that you define, and you say, well, I'm going to separate the state and the control. So I'm going to lift the whole dynamics with a bunch of variables, not the state itself, x, but a bunch of observables on the state. And I'm not even, in this case, going to lift the control. I'm just going to use the linear variables on control. Let's see what happens, right? This is not the most general thing that you can do, but you can certainly then go and try to solve this problem that basically says, okay, find me A and B such that the next value of my lifted observables is predicted best by A acting on psi and B acting on U. It's a solvable problem, least squares. We know how to do it. That's basically DMD, just with control, if you wish, or a modified version of DMD with control. So here are the lifted variables, x and y. Y is one step forward. What do you end up with? Something that we all learn and love in linear control theory, but it's not. To start with, we are with a nonlinear problem, right? We have lifted the problem in some infinite dimensional space, took a finite truncation. It would be exact if the finite truncation lived in the span of the associated eigenfunctions, right? So you can prove conditions under which this works in general, and then we wrap a controller around this. You can wrap an optimal controller of various kinds. Here is the prediction for the system. In this particular case, it's the pendulum, I think. And then in the paper, you also have the van der Pol oscillator. So this is the interesting comparison. Here is what happens if you linearize locally around the trajectory. And here is what happens with the prediction that I have described just in the previous case. So you seem to have, even with strong nonlinearity, seem to have a very nice extended span of things. So once again, this appeared this year. So if you have your favorite problem which you want to do control and you want to test this, let me know, because I'm very interested in understanding what the experiences and limitations are. We did this on the cavity flow, again, the same flow that I have shown you before. And here's what we wanted to achieve. We wanted the red to basically go away. We wanted to stabilize kind of as much as we can of the steady flow. There's low vorticity in the shear layer. And here is how the controller performed. So you should see the blue and the red disappearing over time. And here is the kinetic energy of state error. And here is what the controller does. So first of all, we know what the controller should do in this case. It should actually slow the field down. That is the best thing to do in order to get rid of the sides. It's a high-dimensional problem, but you intuitively know what it should do. It does that. It's very successful in doing that. But how it does it is really remarkable. So look at that. It just basically, it doesn't do something continuous. It gives it kicks, and periodic ones. So is there any sense as to why it should be doing that? Does anybody have an intuitive feeling as to why? And I'll give you a clue. There is a rotation in the system. So the rotation, and the only place where you have the control is up. You're pulling this lid. There is no other control, and you're observing the field only at a finite number of points. Yeah, relatively small number of points. So of course, the controller should give some kick when it can, and it can only control things when they come to it. So it's go with the flow control. You need to wait until something substantial happens, and then optimally kick it, and then let it go again, and hope it's going to come back, because otherwise you have no hope. If something is down here, why would you expect that something that is acting up there is going to have a large effect on that? So interestingly, the physical aspect of this particular control is quite evident if you think about it a little bit, right? The controller should be doing something like that, but it's very, very different from the types of controllers that are designed in linearization around the steady state and LQR. It's extremely different, right? And that shows you its nonlinear nature. If anybody is still having a little bit of a feeling that there is some linearity behind it, this should give you a feeling that it's not, because this is a distinctly nonlinear controller. Actually, it's impulsive. It's kind of badly nonlinear, if you wish. All right, so I'm almost done. I'll tell you that the last thing I'm going to tell you is this power grid model, and the reason why I'm just going to say something about it is that it has dissipation, it has hybrid elements, it has stochasticity, you name it, it has it. It's not a nice dynamical system to start with, and one of the things that people this is New England power grid model, it's hard to come by the data, so this is on the model. There is another paper that we have that, in fact, takes the data from the European power grid exchange and then San Diego blackout. If you're interested in that, you can look at that if you're interested in looking at real data. This is a model, but it has 10 generators, and what is happening today is that you can sense the phase of each of the generators with these phasor units, phasor measurement units that are synchronized by GPS. So in fact, this kind of data is available. One of the things you'd like to know is if there are clusters of generators that act as one. This is an old fundamental problem in the context of power grid, and usually this is solved by linearizing around the rotational steady state, if you wish. So it's 60 hertz here, and then finding the eigenvectors and eigenvalues. Here, we did it in a different way. First, for the finish, I'll show you these 4 of these systems coupled together weakly, and one of them is going to go unstable right now, and then as that instability happens, then all of the other start going crazy, and that's one big Koopman mode that is now going unstable, and in fact, you can characterize it using invariance. Remember energy being an invariant. So here, when we plot a particular invariant here, in the blue region, we get an unstable dynamics, and inside this region, I know the color coding is exactly the opposite way around. Red should really be the dangerous zone where you get instability. But this is in a pretty high dimensional space, and you can characterize invariant sets, as I kind of indicated at the beginning. Now, the last thing I'm going to show you is, so now it becomes kind of the matter of, okay, which things are going coherently together, and which things are staying maybe put and not being affected by this. So you would like to know which generators are in the danger of going together and unstable, right? So for that, you identify the number of modes. Here I have 0.35, 1.10, and 1.30 hertz, and I have plotted their amplitude and phase. And look at how some of them have pretty much the same behavior in phase for 3 different modes, and then some of them have difference. So if you plot phase versus amplitude, and you look at the generators, this is the labeling of generators, that for all of these modes have the same phase and the amplitude, right? So you're clustering them together. You see that 2, 7, 9, and 10 have mode 9 pretty much the same in phase and amplitude, and 2, 3, 6, 7, and 9 have mode 8 pretty much the same. Yes? So from this, I would say, okay, 2, 3, 6, 7, and 9, I'm missing 4, 5, 8, and 10. So 4, 5, 8, and 10 are present here, but they're not present here. So I'm going to put my bet down and say that 2, 3, 6, 7, and 9 are going to oscillate together, and then the other ones are not. So let's see if we go to time traces. So this is purely Koopman operator theory for them. This is 2, 3, 6, 7, and 9, as promised, right? They nicely trace each other. You see that they're pretty close. There are some deviations, but pretty much they trace the same profile. 4 and 5 are clearly different. 8 and 10 are clearly different, which if you did a little bit more analysis of that phase amplitude plot, you would have seen. The remark that I want to end up with is, if you look at this problem, it's nonlinear dynamics. It has a lot of different aspects that are not very clean from a dynamical systems point of view, and yet, by pretty much quote-unquote linear thinking, right? Thinking about eigenvalues and modes and just in this infinite dimensional space rather than a finite dimensional space, you actually get to do the analysis, you get to do control, you get to do these things that we want to do even with high dimensional systems. So if there is one thing I'd sort of like to end up with is, it did bother me originally when I thought about linear nonlinear systems theory that we treat linear systems in an absolutely different manner than we treat nonlinear systems. Nonlinear systems are all about nonlinear manifolds and inertial manifolds and so on and so forth. There is not much of the spectral aspect to it. But linear systems, you get eigenvalues and eigenvectors, and that's what you hang your hat on. In this approach, the eigenvalues, Koopman modes, and eigenfunctions are the things that you hang your hat on, and you kind of can't think linearly. You need to do that mapping that we talked about, which you have a reduced and then you have a lifted, and you need to pay attention to the fact that there is a mapping. But at least the beginning, at the beginning you have this intuition about what these objects are. And so we have extensions to stochastics and estimation. I spoke about control. Actually, estimation is not us. It's Amit Surana at United Technologies. Mitsubishi is doing quite a bit of work. Riken in Japan. A number of entities in Germany. Berlin is pretty big. Australia, New South Wales. There are a lot of references that are not necessarily ours. And so if you have an interest in this, I invite you to either send me an email or read about it and see whether you can apply it in anything that is of your interest. So I know I went a little bit over. Hopefully it was of some use. Thank you.
We're past 5 o'clock. There is a quick question or two.
All right.
So I wonder practically how do you calculate the Koopman modes? So you use DMP, for example, for the flow field, and if you choose the velocity as observables, so basically you calculate the U prime and U star, and then calculate the eigenmodes of the U prime times U.
Yes.
Something like that.
So you have a data matrix.
Yes. If I
And
have
then-
data matrix.
Yes, there is a procedure which involves the Moore-Penrose inverse that actually gets you the mode matrix and the eigenvalues themselves.
So basically, if you choose the velocity as the observables, that is exactly the DFT modes, like the Koopman modes.
Well, so if you choose velocity as an observable, so the question was if you choose velocity as an observable, whether you get DFT modes or Koopman modes. DMD modes are DMD modes, meaning they are an output of the dynamic mode decomposition computation, yes? So the question now is, does this procedure compute Koopman modes? And the answer is, if the velocity observables are in the span of the eigenfunctions of the associated Koopman operator, and you take enough samples, meaning in the limit when the number of samples goes to infinity, then yes, you're computing the eigenvalues and eigenfunctions of the Koopman operator. Hassan Arbabi has a nice paper on that in SciAm. But in general, of course, you have to be careful. There is noise involved. You might not be in the span of eigenfunctions. There is a more general aspect of this that says that essentially what you're following with your observables that are just velocity, let's say, is a Krylov subspace, yes? So you're spanning Krylov subspace. And that, in the limit, when you take a lot of data, is going to span a subspace of the whole set of observables, yes? And that's an invariant subspace. So there are eigenvalues and eigenvectors, or Koopman modes, that are associated with that subspace. And that's precisely what you get if you take enough samples. like every other numerical method, you have the convergence issues that you have to take care of. Very often, if you have quasi-periodic type dynamics, your convergence is going to be nice. 1 over n is a typical result that you get. With the spectral techniques like generalized Laplace analysis, actually that's provable. So you can prove that the convergence is going to go there. To the best of my knowledge, in the context of DMD, except for one case with Milan Korda and myself that is just to come out, that hasn't been shown yet. So that's the range that we have at this point in time. So you have some guarantees that you're computing the correct things with some of the numerical methods that you have out there. I would say when there is a new numerical method, it would be always nice to actually prove something that at least in the limit, you're actually converging to the correct thing. And these are not trivial. These are not trivial results, right? But some of them, they exist, and they are between Hassan Arbabi and Milan Korda and myself.
Thank you.
Yes?
Dr. Mezic, what are the basic limitations associated with the Koopman method? Are there like some problems that it might not be applicable or not might be a solution?
So the question is, what are the basic limitations associated with the Koopman method? There are none. I'm just kidding. Today, if you have a system with a continuous spectrum, we have just started carving into that. So there are 2 papers that are appearing. So for example, the context of fully developed turbulence, right? So far, this has been quite useful in the context when you have some type of point spectrum, some type of pulsing in the flow. And these kinds of things often appear in the flows that you don't necessarily think they're going to appear in, right? So if you have continuous spectrum, but this is more on the computation side rather than theory side, then you have to think very carefully about what precisely you're computing. So there is a paper with Milan and Mihai Putinar that's appearing in Applied Computational Harmonic Analysis just this year, but it's an archive where you can read something about that and something about the issues. This has not been extended to the systems that have convergence to the attractor, so off attractor. So these results are for measure preserving systems, so on attractor, once you have stabilized to some attractor, yeah? But the question is a little bit hard to answer in a specific way, so like it doesn't apply to this. If you're talking about dynamical problems, it's like asking whether state space methods apply to everything, and the answer is yes, they do. It's a framework. What I think about is not the framework itself, which in principle you can write the operator for any dynamical system that you want. I think about where is it useful, right? And so that is almost the inverse question, right? So I only know the places where it's actually kind of useful, right? And the places that are not useful are limited. They always come to the boundary of the sphere and say, okay, where is this stuff not useful? So, okay, I have point spectrum handled by DMD and spectral projection methods. Continuous spectrum is where I haven't been. So let's write some papers. Let's discuss that. That's where we are right now. We are developing this as we speak. But once again, it's more where is it useful than where does it apply? Because a framework is a framework. You can always write it.